Well, the minus, you wouldn't, yes, it's going to change your, yes, I think that's correct.
I just carried them. I didn't put them in until here, if that makes sense.
That answer is incorrect.
So
3, 4, 3, 6, 7. Yeah, I think something down here would have given you a different answer had you got that right. Hello. Yes, you can just redo D part there, okay? So you have your test and the sheet there in front of you about the corrections. Note the corrections are due Friday week for this test, okay? Don't worry about your grade in here, okay? Worry about learning the material. Remember, you've got that PowerPoint that you did, that two-thirds of you did back in November. There's going to be a test this semester, this quarter, and the others of you are going to do it next week. So you've got what should be a good grade for you automatically built in on your test grades here. So don't worry too much about your grades. Your grades are going to work out to be okay. Get the test corrections done because they will help your grade, but more importantly, they will help you learn what you did incorrectly on that. You're free to talk amongst yourselves about how to get to the correct answer. You're free to ask me how to get to the correct answer. But in the end, you've got to put pencil to paper. You've got to show me that you've accomplished what we need to get to the correct answer for those problems and give me an explanation of how to get there and what mistakes you made. So, as Sarah Beth just brought up on the FRQ, you don't have to rework problems parts A, B, and C if all you missed was D part. You can just rework D part, okay? On all the others, they're just a single question, so you need to rework the whole thing. Some of them you'll see marks on your paper where that it was some of your work led me to believe this was what the mistake was that you made. You can start with that, but in the end, you've got to give me a good explanation of what's going on there. Here's what's on tap for the week. Now, I realize that some of you are not going to be here tomorrow or Friday. We will have a lecture tomorrow, but it'll be very brief, shorter than what we're talking about today. And then you're going to have some time on Friday to work on FRQs, to work on test corrections, to work on homework. So you will miss one day of lecture, those of you that are going to be going on the retreat, but you won't miss 2 days of lecture. It's looking very unlikely that we will get in a test before the mission trip next Thursday. So what we're probably going to do is come back, and the week after the mission trip, when you come back, we'll come back that week, do some review of this stuff, and have a test over DiffyQs on March the 11th. That's probably what we're looking at right now. So we are going to be talking about 36 here, so if you haven't downloaded that yet, you can download it. Last time we met, we were talking about something called differential equations. What are differential equations? Yes, they are DiffyQs. No. How do we look? Well, if it's an equation, means it's got a solution. It's got an equal sign in it, okay? What makes it a differential equation? Right. We have equations with derivatives in them. Normally, it's an equation that relates the derivative to something else. So it might be something as simple as y prime equals x. It might be something like y double prime minus y equals y prime. It might have multiple derivatives in it. But if it's got a derivative in it and it's an equation, then it can be classified as a differential equation. We also learned how to represent differential equations graphically. If we're going to do that, what does it look like? What do we call those things? What do we call slope fields, okay? And if you go back and look at your notes, and if you recall, with slope fields, you're just figuring out what the slope, what the first derivative is at a bunch of points, and drawing a little line to signify each of those points. This is what the equation, this is what the slope is. How can a slope field help us in relation to differential equations? What were we able to do once we once we had a that's right, we could kind of sketch what we thought the graph might look like through there, because we could almost like a connect the dots. So that's how slope fields are important. Slope fields are much more interesting now in the last 20 or 30 years, because you have things like your iPad and like your calculators that can draw them in great detail. Well, today we're going to talk about how do we solve differential equations. Most of the time, with what we were talking about at our last lecture, we were talking about, is this a solution? So I gave you something and said, hey, is this a solution to it? Much more interesting and much more important is, how do we solve differential equations? The only method we're going to learn to solve DFQs is by separating the variables. Now, what does that sound like we're going to do if we call separating the variables? Kind of like substitution. Separate. We're going to separate. We're going to tear apart, get the variables apart from one another. Okay? So let's take an example, being the first example you've got there. We've got a differential equation there. Y prime equals 2x over y. Now, I'm going to walk through the steps that I recommend, because I think it will help you to visually see what we're doing. First of all, anytime I've got y prime, I'm going to first change that to dy over dx. It's just going to make a little bit more sense if we can do that, to represent our variables as dy over dx. Now we want to think of this as algebra, and we want to get everything that's got a y on the left side of the equation. And I'll explain why the left in just a little bit. But everything that's got a y in it, we want on the left side of the equation. So if we do that, we get y times dy on the left equals 2x times dx on the right. Now, what we've got written there, does that look familiar to you? What does it kind of look like? Maybe. If I showed you just this left side of the equation, you'd say something's missing, wouldn't you? Well, what do we normally see when we see y and dy there? We normally see a symbol to integrate. So if we want to solve this at this point in time, we need to integrate. Well, if we integrate the left side, what do you think we should do over there? Integrate on the right side as well, okay? So now by doing that, now we've taken our differential equation and we've made it into two integrations. Well, can you integrate y? And going the wrong way. We get y squared over 2, don't we? And what do we get on the left side? Or the right side, the other side, whichever side that is. We get x squared. Very good. Now, we don't have limits of integration on either of these, so what does that tell you we should have in addition to that? A plus c. Now, do those c's have to be the same thing? I mean, are those c's, does the c that's on the left side have to be the c that's on the right side to get us back there? No, they don't have to be. So we could really mark them as c sub 1 and c sub 2 to recognize that, hey, they're two different c's. And in reality, the way we're normally going to write this is we would just simply want to write one constant of integration, and we would write it like this. Because think about this equation that we've got right here. With this equation, if I subtracted c1 from both sides, I'd get a different c. So this is the way you would normally see this written, is just y squared over 2 equals x squared plus c. Writing a c on both sides is not incorrect. It's just not the normal way to write it. And you could even see this written as y squared equals 2x squared plus c. Do you see why I can do that? Good question. Would I take the square root out? If you take the square root out, you're going to wind up with two solutions there. You'd have plus and minus the square root of 2x squared plus c. You could do that, but customarily we'd leave it just like this. Customarily, that's what we would expect to be written as our answer there. Now, does anybody have a problem with the fact that I didn't multiply this red C by 2 to make it into this black C down here? Because multiplying it by 2 just makes it into a different constant. So even though it says it's the same letter, it might not be the same letter here, okay? Or might not be the same number. So y squared equals 2x squared plus c is a solution to this differential equation. And how can you check to see that it's right? Very good. If you take the derivative. So if we were to take the derivative of this thing right now, we would get 2y y prime equals 4x. So y prime equals 4x over 2y, which becomes 2x over y. So, boom, it does work. We're back to where we started from. In a sense it is, yes. Okay? So let's look. Is this a differential equation? Yes. Okay, then solve the differential equation. See if you run into any difficulties with attempting to solve this differential equation. Separate the variables. Get everything with y's on the left. Get everything with x's on the right. And then integrate both sides. Gabby, did you want any lunch? Okay.
Well, either I did it wrong or I wasn't even trying to find it.
Okay, when you separate it, I get dy equals 6 minus x dx. So now we're going to integrate both sides. What do we get on the left side? Y. Because we're integrating just the number 1. What function with respect to y has a derivative of 1? It would be y equals, the antiderivative for 6 is 6x minus x squared over 2 plus c. We comfortable with that? We would integrate both sides, and this is just going back on the right side. We're using the power rule for 6 and for x. Going back to using our power rule, and that's where we get to our answer. Questions, comments, observations? That's right. This is exactly what I wanted you to see. Solving differential equations is nothing more than integrating. So we're doing the same thing we've been doing for the last 2 months. We're just using it in a little different, we're getting to the point of integrating by a little differently than before. Well, how is this problem different when you just look at it? It's minus y, okay? Now, is that going to give us a dramatically different answer? Well, let's see. This is what we get. But now, what's the problem with what we have written so far? Okay, we need to get the y on the other side. And here's where we've got to understand something. This 6 minus y is being multiplied by dx. I can't just add y to both sides. Okay? I have to divide by this 6 minus y. So I'm going to have 1 over 6 minus y times dy equals dx. Because I don't have just a y on the right side. I have the quantity 6 minus y multiplied by dx. I'd either have to distribute this to begin with, make it 6 dx minus y dx, and then I still couldn't add a y to both sides. I'd have to add a y dx. So the proper thing to do is I've got to divide by this entire quantity 6 minus y. Now, when I integrate this, the right side's easy, isn't it? On the right side, we get x plus c, okay? What's going to happen over here on the left side, integrating 1 over 6 minus y? Yes, when you look at this, hopefully you're going to see I've got something in the denominator raised to the first power, so that tells me LNs. Now, for many of us, you're still going to need to write out your u substitutions. So what is u going to be equal to when I'm integrating this left side? Very good. U is 6 minus y. All right, so if u is 6 minus y, then du is negative 1 dy. Well, I don't have a negative 1, so what am I going to do? Divide by negative 1, so I'll have negative du equals dy. Now, when I substitute in, I have an integral sign and a negative sign and a du. I'm putting that in for this right here. Then I've got 1 over u. Well, how are we going to integrate 1 over u? It becomes ln, so I have minus ln absolute value of 6 minus y equals x plus c. Okay? Now, yes, sir.
Oh, I have a question.
Yes, sir.
Why don't you just like integrate the y on that side to get like y squared over 2 and then add it to the other side?
Why don't we just integrate here? Because we're integrating with respect to x over here. See, it's got a dx. Even if we're looking at it right here, this says if you take this dy over dx as saying to integrate, it says integrate with respect to x. So if we've got something other than an x over here, we'd have to treat it as a constant number. And we can't get to the solution there. Now, this is a lovely solution, but that's not the solution I want you to have. That anytime we do not like to leave LNs in our answer. They are challenging to work with. So, what do you think? Give me some suggestions on what we should do here. I actually want my answer needs to be y equals something. That's how I want my answer to be. We can do e's. I would get rid of the negative sign out in front of ln first. How can we do that? Yes, so what I would start off with is ln of 6 minus y equals negative x minus c. Oh, it could be plus c. It could be plus or minus c. Neither one that you write down is wrong here, okay? The only thing I would say is be consistent with it. All right? Because, Robert, if you could leave it as a minus c and Chase leaves it as a plus c, if you were to actually figure out what c was, hopefully y'all come out with two different answers. Because yours should be negative, your c should be negative something and his positive or vice versa or something like that. But as long as you're consistent, it's okay there. Now that we've got the ln by itself, now we can introduce the e's. Does anybody know what this looks like once we introduce e's? Yes, it's e raised to this power on the right, e to the negative x minus c equals 6 minus y. E to the answer equals the argument. Yes, sir.
Do we have to keep the absolute value so the domain is restricted?
Good question. Do we have to keep the absolute values in here? And the answer is technically yes, you do. But most of the time, if we're working with a problem like this, we would be told that the domain is, what's the domain got to be? Less than 6? Yes, the y is less than 6. Then it would not matter. You follow what I'm saying? We would normally be given a restricted domain to begin with. But you're right. If there's no domain given, we need to leave it in the absolute values. And that's the process that we would use to get rid of the LNs. This, believe it or not, this bottom thing is an easier problem to work with than the top thing, than the LN thing, okay? So that's the normal procedure that you're going to find here. You're also going to find be it good or bad, that many interesting differential equations have e's in them for their answer. The solutions often are exponential in math. So don't be surprised that you have that to deal with there. All right, let's look at this problem here. See if you can solve this. Y prime equals the square root of x over 7y. Separate the variables and solve that equation for me, please. Separate the variables and solve that equation.
How simplified do you want it?
I don't know. How simplified can it become?
Anything Y squared.
Yeah, let's get it to y squared.
Unless I did it wrong.
I think that would be logical. Let's get it to y squared equals something.
It doesn't matter. It's like the red team. Literally.
All right, I got 7y squared over 2 equals 2/3 x to the 3/2 plus c. You could keep cleaning to 7y squared equals 4/3 x to the 3/2 plus c. And you could divide everything by 7 even if you wanted to, but I think that would be...
I just flipped it.
Yeah. You could, yeah, and make it 4/21 x to the 3/2. So, yeah, it is 4/21. So, problem solving that for you peoples? All right. Well, and yes, it does. But if we multiply this c up here by 2, it's still just a constant number. So we normally just write it as the letter c there, okay? We could divide through by 7 and get y squared equals 4/21 x to the 3/2 plus a different c than either of these c's here. So that would be, any of these would be acceptable answers. What I would say is you need to be able to recognize any of these as an answer in a multiple choice scenario. Okay. All right, questions, observations? All right. The next one, solve by separating variables. I want the answer to be y equals. The domain is restricted such that you can get rid of absolute values if you were to have them in there. So I want you to wind up with a y equals for an answer there. See if you can jump through the algebra hoops. Of course it is.
Y by itself?
Yes, y by itself, please. I think we can do that. I think we can get to that point. He thinks we can get to that point. Very good. Isn't that pretty looking? I'm afraid it is. It is. I'm going to show you a different potential answer just for the fun of it, though. It is on everybody else's, buddy. I don't know. I mean. Go back and check. I mean, all of them have it on there. All right, is everybody comfortable with that so far? All right. So now we can do this, can't we? E to that equals 1 plus y. Agreed? Now, here's... All right, now we've got to get... that answer's not on your multiple guess. Okay, even when we subtract a 1, it's not there, okay? So how can we rewrite this to be the same but look differently? I want to focus in on this part right here. If we were to break that apart, what would it look like? And here's where I'm getting to here. If we've got x to the 2 plus 3, what's a different way to write that? Yes, so we could rewrite this as e to the x squared over 2 times e to the c equals 1 plus y. Would you agree with that? All right. Now, this is where if you're really, really concrete, your mind's about to get blown. So we can just change this into c e to the x squared over 2. Because this c that I just wrote right here, this c is not the same as that c up there. Okay? Like I said, this is where your head starts hurting. Imagine what this would be like at the end of the day. Because e to the c, we can write down here, c e to the x squared over 2 equals 1 plus y, or we could make it y equals c e to the x squared over 2 minus 1. Now, I want you to take a look at this. It's not c minus e squared, it's c e squared. It wasn't e squared, it's c e. Come on, really? Jeez. Write something down correctly. X squared over 2 minus 1. Does that equation look like anything you've ever seen before? If you go back... Kind of like the y-intercept or whatever it is. All right, it looks kind of like a y-intercept, y equals mx plus b. I bet if you go back and look at your exponential equations, when you studied exponentials last year in Math 102, you probably saw quite a few exponentials that had a number out in front and e to a power. Y'all remember the PERT formula?
Oh, yeah.
PERT?
Yeah.
Principal equals interest to the rate times time power for compound continuous interest. Half-life, chemistry, half-life is also the same thing like that. So most exponential equations have this type of look to them, a number in front, e to some power. And so hopefully you can put 2 and 2 together. So if this is what most exponential equations start off as, most exponential equations are solutions to differential equations. So half-life is differential equations. Continuous interest is differential equations. Those things are related to one another because this is why, this is how we get to the solution. And that's what you're going to find, I believe, on the next slide. Nope, not the, we'll get there. In a couple of slides, we're going to get to a little bit more applications to it. But let's suffer through this thing first. Solve by separating variables. Now, this is the first time we've had something like this, xy plus y prime. So we know we need to change that to xy plus dy over dx equals 100x. Now what do you think we should do?
I do 100x minus xy and then pull an x.
Very good. You do need to be sure that you isolate your derivative first. dy dx, if you isolate it first, then you should be able to solve this. And as Sarah Beth said, now that we've got it isolated over here, we can factor out an x. X equals 100 minus y. And now we should be able to solve this just like other equations. 1 over 100 minus y equals x dx. That should be a solvable equation for you. I want you to get y equals something.
1 over 100 minus y, because if you move the dx to the other side, you move the dy.
Which dy?
All right, if I multiply this side by dx and this side by dx, those things cancel. Oops, it should be dy now. Yes, it should be dy. That was your question.
No, it was the one that I figured out.
Okay, we've got to divide by this 100 minus y on both sides. And now we get something that we can integrate. Again, if you need to write down your u substitution to do this left side, there's nothing wrong with that. Don't be afraid of that at all. Hopefully, over time, you're going to get to the point that you don't have to write it down because it takes you a little bit of time to do it. But I'd rather you write it down than not get it correct. So it's minus the ln 100 minus y equals x squared over 2 plus c. And if you get to that point, what should be our next step?
You can put the c in
Yes. 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 There's lots of things you could do here. We could do the e's now, but if we do the e's, we've still got this pesky minus sign out here to deal with. So I would get the minus sign over first. Negative x squared over 2. And I don't care if you write it as plus c or minus c. It doesn't matter.
What are these rules about negative ln?
What do you mean now?
What happens if the ln is negative?
If the entire ln is negative, it just is. Now, this number in here cannot be negative. Okay? You can take this, I think you're talking about the properties. I can take this minus sign up here and make it into a power if I want to. So I can make this ln of this quantity to the negative 1 power. Is that what Chase was doing there? Okay. There's nothing wrong with doing that, okay? If you do that, you're going to wind up with e to a positive power equals 1 over 100 minus y, which you could eventually get back to the same thing. So there's nothing, as long as your algebra is sound, either one of them will be okay. Consistency is going to be the key for you. So we could make this c e to the negative x squared over y 2 minus 100 equals. Okay, all right, I'm about to get there. So I'm going to get y equals 100 minus c e to the negative x squared over 2. All right, but see, I got rid of the negative over here with the y, so if I divide everything by -1, then that's the number in front of c becomes negative. It would be fine to do that also. Either answer would be, if you have this written for an answer, it would be fine. If you had 100 plus c e to the negative x squared over 2, it would be fine. Again, in either case, if we solved for the c, you should come up with two different answers. They should vary by a negative sign there.
Which should we expect to see as a multiple choice?
I don't think this test is multiple choice. I think you're going to get to actually work these out, and I'm going to say get to y squared equals or get to y equals or something like that, if I remember correctly.
You don't think these will be multiple?
No, I don't think. Yeah, I don't think so. I think those that are multiple choice are going to be like the ones we will look at tomorrow, where they are more application oriented. Okay. Now, this is a big picture item here that we're about to look at. This is a rate of change problem. So let's see, first of all, can you translate that into an equation? The rate of change of n with respect to s. So what does that mean? dn over ds. Notice it said capital N is proportional to, what does that mean? Equals, what does proportional to mean? We have a number here, a constant, k, 500 minus s. Okay, the rate of change of s is proportional to 500 minus s. See if you can, well, there are, but k is a constant number. It's an unknown, it's not a variable. Yes, it's just like a c. I wrote it as a k because we normally write is proportional to, we normally write the constant of proportionality as a k. Now, so let's wade through solving this. We get dn equals k times 500 minus s ds. That almost cleaned up too nicely, didn't it? So now if we were to integrate both sides, what would we get on the left? N. And we could actually pull this k outside if we wanted to and just know that it's going to be a k times, how do we integrate 500 minus s with respect to s? What's the integral of 500? 500s minus, what's the integral of s? Very good. Plus a different c out there. Because when we integrate, we do get a c on the end. So now we've got an equation that we could solve. Now we have changed this differential equation into something. And if we were given the correct information, we would be able to solve this out. If we knew that there were 30 of these things when s was 0, then suddenly we could figure out what c is, and then with another piece of information we could figure out what k is. Any questions about that? All right, I think I've got one last problem. Yes, actually, two last problems. This one, the rate of change of v is proportional to v. The rate of change of v is proportional to V.
DV over V.
dV dt, the rate of change of V is proportional to V. So what's it going to be over here? kV. This is a crucial problem for you, okay? If you solve this problem, you will just solve numerous DFQs that you're going to see, and you never have to solve them again. dV over dt equals kV. So let's solve this problem out. And I know we've got this other data here. When t equals 0, V equals 20,000. When t is 4, V is 12,500. What's the value of V when t is 6? We'll get to all that in a minute. Solve the DFQ first. So we say dV equals kV dt. Now, I am going to just divide by V. Is it wrong to divide by kV? No, it's not. It's just easier if you divide by V, okay? Can anybody tell me why they think, why it may be easier just to divide by V?
You don't have to worry about the K being on the outside when you put it.
Yes, now when we integrate this, we just, is that a straightforward integration, 1 over V? What's that going to be? ln V. So that's easier. If we've got that K in there, it's going to mess with things there. So it's easier to do that. Now if we integrate, we already said over here we get ln of V. What do we get when we integrate K? KT and the sunshine band. KT plus C. Right? Now, what is V standing for in this problem? Well, we don't know. I mean, I was going to say it's volume. I don't know if it's volume or not, so we can't really say. But we're going to assume that V is always positive, so we're going to throw away these absolute value bars here, okay? And if you think about it in real life, if V is the volume of something, it's always going to be positive. Or if V is the number of something, it's going to be positive. So we're going to assume it's positive. It is e to the kt plus c equals V. And then we know that this is really e to the kt times e to the c. So we're going to change it to V equals c e to the kt. Yes, this is the PERT formula. Anytime you see the rate of change of V is proportional to V, the rate of change of T is proportional to T, the rate of change of A is proportional to A. That first statement up there says this is what it's going to look like. If you've got this, you can wade through it, but you can know that your answer is going to look like this. Now, our next task is to finish off the problem. So we've got V equals CE to the KT. Now this, from here on out, should be a bad memory from last year. When T equals 0, V equals 20,000. Does that help us? Bottom line, we need to figure out what C is. We need to figure out what K is, okay? So when T is 0, V is 20,000. Right. If we plug those numbers in, 20,000 equals C e to the 0, right? Because K times 0 is 0. Well, e to the 0 is the number 1, so C is 20,000. Boom. All right. So now we can rewrite, we've got V equals 20,000 e to the KT. Very good. When T is 4, V is 12,500. Can you do something with that? That's right. So we can say 12,500 equals 20,000 e to the 4k, right? Well, tell me how to solve that. Divide by 20,000. So I'm going to get 125 over 200 equals e to the 4k. And yes, you're going to want a calculator for this bad boy. So how are we going to solve this thing that's got E's in it, peoples? ln. So now we can say the ln of this number, which I'm sure will reduce, but I'm not intelligent enough to do right now. 5/8? Oh my goodness. Okay, so the ln of 5/8. So then we can figure out that k equals the ln of 5/8 divided by 4. Do you see how I got there now? I know I did some stuff in my head. Kevin did the 125/200, reducing that down to 5/8. And then to find k, I just divide by 4. Crucial thing here. If you pick up your calculator and start punching right now, write down 4 or 5 decimal places. If you just round it to 2 decimal places, you're going to blow your answer way out of proportion. So if you pick up your calculator right now, know that you've got to use several decimal places. So now, and I'm about to stop, I promise you. I know y'all are tired of this. So now we've got this. So with those 2 steps there, we have changed and found out that V equals 20,000 E to the ln of 5/8 divided by 4 times T, right? And now we can plug 6 in there and figure that out. If you're really smart, you can go ahead and simplify this and get rid of the E and the ln. V equals 20,000. That's the same as E to the ln of 5/8, right? Times E to the T over 4. Couldn't I break it up that way? Because that's ln times 1/4 times T. No, I couldn't do that, could I? No. It would be this. Because when I raise a power to a power, I multiply, right? Well, what's E to the ln of 5/8? Yes. Yes, if I multiply these 2 things, I get that. But here, the reason I'm doing this, because y'all are smart people, number 1. But number 2, what is this E to the ln of 5/8? 5/8. So you could simplify this to 20,000 times 5/8 to the T over 4 power. Now, I don't know, that should give you the same answer as if you work with the top one up there. But those of you that like to look at CalChat, it's probably going to have it simplified down to something like this, and then plug 6 in there. So you're doing 5/8 to the 3/2 times 20,000 and getting a number there. That sounds about right. So that's about how much. So y'all have y'all studied fruit flies yet? Okay, y'all aren't biology people, okay? Biology people have studied fruit flies. Y'all, half-lives, fruit flies, exponential growth and decay, all of those things, carbon dating, those things are all related to this, and we'll get to some of those applications tomorrow, okay?
So the T over 4 there is the exponent?
Yes, it's 5/8 to the T over 4 power.
Wait,
Now,
I thought it canceled out just 2 of them.
all right, this E and ln cancel out and just make this 5/8 to that power there. See, I could rewrite this thing right here as E to this power here, then raise that to this power up here. Because when you raise a power to a power, you multiply the exponents. Okay, people, you have some FRQs, you have some test corrections, you have some homework, and you've got a WebAssign due next week, so you don't really have to worry about that WebAssign yet. So you've got things you can be working on. Help is officially